Hello, my name is Katherine Playfair, and I will be talking about the role of bioplastics in reducing food waste. So I am a joint MS MBA student, like many/all of us here today. Before Stanford, I worked as a data scientist at McKinsey's sustainability practice, and my undergrad degree is in applied math. Much of my time at Stanford has been spent researching how the US can divert more food waste away from landfills due to the methane emissions associated. And I've collaborated with a number of academic labs to understand what technology is at the forefront of this problem. A little bit about the why. I am an avid at-home composter, and many call me a leftovers queen. I love cleaning out the fridge. And I'm looking to craft a role post-graduation in the circular economy sector. So what we're going to talk about today. First, what's possible? So how do we actually reduce food waste with bioplastics and bioproducts? As well as integrated lipids biofuels, which is the venture that I worked with over the past several months, who is doing this today. The second piece is where we are, so ILB, that venture, how they're actually doing this and what their costs look like, because that dictates what the market could be and the potential impact. As well as investors, how hesitant they'll be, how excited they'll be about this opportunity. And then what's next? How can we find the right partnerships to ensure survival? We're not at cost parity today, but we need to get there. And then in order to get there, reducing your high cost levers and optimizing your yields. So let's dive in. Bioplastics, I like to call it a win-win. We can not only reduce food waste, but we can generate biodegradable and biocompatible products. The reason food waste is so important is if it were a country, it would be the third larger emitter of greenhouse gas emissions. It's a huge contributor to climate change. And the way we can address this with bioplastics is through the process of biomanufacturing. And that essentially takes any organic feedstock, so high in carbon, that could be either food waste or any plant matter. It goes through the biomanufacturing, which involves fermentation, and you create bioproducts. That is primarily in the US, pharmaceuticals, but we can also produce biofuels, chemicals, and of course, bioplastics. So integrated lipids biofuels is a venture that was started out of Washington State University. They incorporated in 2018, and since then have seen a ton of success and growth. So they recently were awarded grants from the Department of Agriculture, SBIR grants, which are small business grants. And then they were accepted into an accelerator incubator that's called Plug and Play. Earlier this year, they brought on their first full-time employee, and then I began working with them in August of this year to support the commercialization of their bioplastics. And the first step in doing so is looking at the techno-economic analysis, which, to simplify it, the process, the costs, the outputs. And so before we get too lost in this process, let's just remove the equipment and look at inputs and outputs. What I found is that you'll see that the red circles are the costs, the green circles are the revenues. And what I love about this process is that the feedstock, so this input is food waste, and it's a revenue generation source. So not only are you receiving money when you sell the plastic, but you receive money when you take that feedstock to create the plastic. And so what this essentially does for you, which is why I think that this process is really promising, is you have a super low raw materials cost. So relative to your conventional petroleum-based plastics, which raw materials are going to be $1.05 per kilogram, you have bioplastics, which because of that revenue that you're generating from the front end, 70 cents per kilogram. And these are super cheap, so this is really promising. Add in utilities, still looks great. Now the problem arises when you add in OPEX, CAPEX, so the operations and the capital costs. Now, a lot of the petroleum-based plastics today are produced by the Dow, the Exxon. Huge companies have invested billions of dollars and decades of research to minimize everything else that goes into your plastics. We don't have that luxury with bioplastics, and it is a very risky, resource, time-intensive process. And this does not even include novel technologies, unforeseen costs. For example, fermentation is very sensitive. So if you have microbes, which is inherent to the process, they can mutate, this can cause challenges. So the scaling up of this technology is really inherently risky. So what does this mean for developing a product? Investors are going to be pretty hesitant because we need to get from $5, $10 a kilogram, depending on where you're at, to $1.50. In order to do that, near-term partnerships will ensure the survival of ILB until we can get to cost parity. And that's both on the investors and the customers. So for the investors, we need investors who are willing to provide patient capital. They have to be willing to deal with technical risk. And ideally, they would bring expertise for scaling new technologies such as this one. ILB is already working with government agencies such as the Department of Agriculture, but incorporating other foundations, impact investors, family offices, those who have a lot of patient capital to invest in developing this technology. The second piece is customers. So we need people who have enough cash flow to pay a premium above petroleum-based plastics. That's somebody who has a good amount of cash, maybe even Dow could become a partner there. They need to be willing to work with a startup that has growing pains inherently, and ideally they would obtain value from the biocompatibility and biodegradability of this plastic. One example is thinking about if you have food packaging, petroleum-based plastics do have some toxins, especially when heat is applied, and bioplastics wouldn't suffer from the same issue. So in order to do that, not only do we want to get the right partners in place, we obviously have to get that big OpEx and CapEx bucket reduced. So we need to invest in reducing our costs and maximizing our yields. I won't go through each of these, it's a bit nuanced, but these are the efforts that are occurring in Pullman, Washington today at the lab to make sure they are minimizing the highest cost efforts in the technology development. And then on the right-hand side, you'll see that we're trying to optimize yields. There are a number of different stages in this fermentation process, and we need to make sure that we get the most bioplastic from our input of food waste. So looking at each of those stages and trying to maximize yields. And of course, the holy grail here, the target is to achieve a production cost of $1.50 per kilogram. Once we can do that, you can start to really offset and displace the petroleum-based plastics industry. So I'm very excited about the potential there. And so with that, I would like to thank my advisor, Matt Cannon, a professor here at Stanford, who has been an incredible mentor to me through this journey, as well as Dr. Shulin Chen, my client, who has been the inventor of a lot of this technology over at Washington State University. Thanks.
Just curious, what would be the sources of food waste for the feedstock material?
Yeah, great question. So all different organic feedstocks can be used. The one that has actually provided the highest yields of the acetic acid, which is the feedstock for fermentation. So the highest yield of bioplastic has been cafeteria food waste from Washington State University. So it's often a very high fat food content, and it needs typically diversity of nutrients in order to be digested effectively into the amino acids. So any high diversity, lots of different types of food is the best.
Great presentation. Wondering if you're planning to help this team post graduation, get those costs down and help them with find patient capital and customers, or?
Yeah, it's a great question. Based on a lot of this research, it seems like the biggest efforts to get this closer to widespread sales is going to be the tech development, and that is not my forte. And so I will be keeping an eye on it and keeping in touch with the Washington State team.
I was intrigued by your positive revenue stream from the acquisition of the organic waste. How did you get those numbers? Because the reason I asked, when I've looked at other biofuels, the companies pay to get rid of the material, but there's a high cost of gathering it, picking it up, and bringing it down, which compensates for a lot of that. But what was your logic for getting a very high revenue stream from acquiring that organic material?
It's a great question. So two things come to mind. The first is many of the biofuels companies are using what is called an industry fog, so that's fats, oils, and greases. Yeah. And because there's a bigger and better known market and it's easier to convert those into biofuels, they're not as expensive to discard, and oftentimes you can get paid for it. Conversely, there aren't as many applications for diverse, very contaminated even food waste, and so it's lower cost. And the second piece is This is raw materials assuming on-site feedstock. Transportation is going to be a huge cost, and that was not incorporated into the raw materials portion. Yeah, good question.
Not including that is an important part of answering my question.
Yeah, and this is assuming a smaller plant where the WSU, Washington State feedstock is on site already, that food waste. Good question though. Transportation is huge.
Okay.